Okay, in this video I'm going to show you how we demonstrate equipotential lines in an electric field, in a uniform electric field. Right, DC power supply, got it all the way up to top, 13.50 volts. Now the electric field is going to be between these two plates here. Okay, just a sandwich tray from, you know, like a takeaway. But yeah, in it we have two pieces of polished copper connected to crocodile clips. They're lovingly stuck in using blue tack, as you can see, and we've got a ruler across it because I'm going to measure the potential at various distances across the uniform electric field. So the uniform electric field is going to be between those two parallel copper plates. Okay. Now, if you know the distance, which is 15 centimeters, and you know the potential difference, which is 13.50, first thing you can do, you can find out the field strength, can't you? You can find out the field strength between the two plates. So that's what I want you to do first. Right, got a voltmeter. Now the voltmeter, the earth, the 0 volts, is connected to this side, which is the 0 volts here. On the positive side of the voltmeter, I've got a probe, okay? So, looks a bit rusty, so let's just give that a bit of a, with sandpaper, give that a bit of a clean, because obviously we want as clean an electrical connection as possible. Right, now if we place in, okay, if we place in the probe into the electric field, it's not going to read anything because the way voltmeters work, they need a tiny current to flow through a known resistance, and the voltmeter does V equals IR. That's how it measures voltage. So we need a current to be flowing when we stick the probe in, and that is done using copper sulfate solution. Copper sulfate, because it is a nice conductor, there's a lot of ions dissolved in this thing here. So yeah, it's looking suspiciously like electrolysis at the moment. I think the chemists will like that. Anyway, right, so voltmeter here. Now if we connect the voltmeter to this side, okay, we should be getting a reading of 13 volts. Let's try another. Okay. Let's go with one that definitely works. As you can see there. Okay, so we'll use this as the probe. Right, so if it connects here, this is now measuring the voltage, the full voltage across, as expected. Okay. So if I stick it into the solution, about 13 volts. If I can put the probe here, this will be measuring 0 potential difference. Right, halfway between, this is the interesting thing, now there's 15 centimeters across here, so if I go bang in the middle, 7.5, we have a potential of 7.11 volts. Now, first thing I want to demonstrate here, we can actually plot the equipotential lines. So if we move, remember, equipotential lines are lines along which the electrical energy is constant. So they are lines along which the potential is constant. So if we move parallel to the plates, the potential, as we can see, stays constant. We go halfway down. If we go a quarter of the way across, we're going to have a potential, if we stick it in the middle there, we've got a potential of about 4 volts there. But if we go up here, if we go along an equipotential, the potential and therefore the electrical energy of any charges at this point is constant. Right, but if we go across here, so 0 if we touch the plate, and then move across slowly, as you can see the potential increases up to the maximum value. Okay? which is about 13.5 volts. Right, I'm going to give you some results because there's a quick graph I want to plot. So, independent variable is distance from 0 volts plate. Dependent variable is going to be voltage. Are you ready? So, distance of, I'm going to come around the other side because that's going to be a lot easier. Distance of 0, potential difference 0. Right, distance 2 centimeters. Voltage 2.61 volts. Distance 4 centimeters. So 4 centimeters into the electric field, 4.29 volts. Distance of 6 centimeters. Potential difference of 5.86 volts. 8 centimeters into the electric field from 0 volts, 7.32 volts. 10 centimeters, potential difference 8.92 volts. What are we on? That was 10, wasn't it? 12 centimeters into the electric field, 10.44 volts. And last one, 14 centimeters into the electric field, 11.80. 11.77 maybe. And then last one, 15 centimeters into the electric field. We'll go with 13.35 volts. Okay, well, you've got a range of values there. Dead simple. I want you to plot a graph of voltage against distance from the 0 volts plate.